Good afternoon, everyone. My name's Cameron Cox. I'm a senior at Western New England University. Today's presentation will be about the prevention of stress-induced failures of pre-stressed concrete crossties with a focus on engineered cementitious materials. I'd like to acknowledge PIs Dr. Changhoon Lee and Dr. Moochul Shin, as well as other students who've worked on this project, seniors Jacob Eberly and Andrew Masulo. Here's the outline for today's presentation. First, I'll start off with the background and motivation, followed by our work with engineered cementitious materials, and I'll wrap it up with the future works. As far as railroad track structure goes, North America has always used wooden cross ties in the past. These are very economical, yet not the strongest in terms of durability. Countries now are progressing more towards concrete cross ties, and this is because they've found to have a longer service life, upwards of 50 years, less maintenance efforts, and better durability than the competitor wooden cross tie. Although concrete cross ties are stronger and have a longer surface life than wooden cross ties, there are some performance errors that are seen in certain cases. Here's an example in the New England region, right here in Massachusetts. The Massachusetts Bay Transportation Authority is filing a $90 million lawsuit against a concrete cross tie company out of Denver. They installed cross ties on two lines on the Old Colony Railroad, and the service began back in 1997, and during inspection they found many cracked and broken cross ties in 2007, so 10 years later, and that's nothing compared to the advertised service life on these cross ties, which is upwards of 50 years. And so for safety of the passengers, the MBTA had to require trains to decrease their speed from 70 down to 30 in these areas where cracked ties had been identified, and they even had to replace defective ones with wooden cross ties. And overall, there was a reported 147,000 defective cross ties. Here are some of the most common concrete cross tie damage types found in the field. One is rail seat deterioration. This is when the bottom surface of the rail rubs on the top of the concrete cross tie, creating a deteriorated surface, which in turn tips the rail. Another is horizontal cracking due to the pre-stressed wires inside of the concrete cross tie. Another one is ASR reaction. Another is the structural failure of center binding, and also many of the other unpredictable complex loadings that create moments and shear stresses that can't necessarily all be considered in design. There are a couple things to consider when trying to create a durable concrete cross tie. The first one is a concrete with high compressive and tensile strengths. This is to offset the complex loadings conditions that they see in the field. Another one is to create a concrete that's durable. This is important because of all the abrasion that it sees due to the rails. And another one is a concrete with a high fracture toughness. This is important to help mitigate crack propagations when they do happen. So given some constraints that are needed in order to achieve a durable concrete cross tie, we were able to generate a vision of our engineered cementitious material, also known as ECM. So we wanted to generate a regular concrete mix that would be sufficient enough to meet those performance needs in concrete cross ties. Also, to use aggregates that can be readily available to industry. And we also want to include coarse aggregates in our concrete mix. This is a large cost benefit due to the fact that traditional UHPC is 20 to 25 times more expensive than regular concrete. Right from day one, we've always wanted to keep the ECM marketable, being that our vision is more industry-based. ECM would be a good candidate for high-rise buildings with small column designs, also precast concrete girders for bridges. The strengths we've achieved with our ECM have been 3,000 to 5,000 psi stronger than typical concrete used in bridge girders. Thus far in our research, we've been able to tackle achieving high compressive strengths and tensile strengths as well as durability. To get high strengths, we've focused on lowering the water to binder ratio, adding slag and silica fume along with a cement, and creating a well-graded aggregate distribution. And the well-graded aggregate distribution also points to durability because it creates a dense concrete that's very smooth on the edge surface, so that helps with abrasion. Durability is also improved because of adding slag and silica fume due to their fineness. And it's also an environmentally friendly item because it replaces 20% of our cement by mass. Over the last 2 years, we've created very many different ECM mix proportions. The graphic on the right shows our mix proportions by volume, and this is kind of just an overall general range that we've followed for all of our mixes. So to start off, by the end of our research, we've narrowed down our paste volume to be less than 40%, and this is to reduce shrinkage in our concrete. So within our paste volume, cement is right around 13 to 16%. Silica fume is 4 to 5%, slag is 5 to 6%. Those are again by volume. So for cement, we've tested both type 3 and type 1. High strengths were achieved by type 3 and type 1 due to the heat of hydration. Some type 3 mixes were not able to be successfully mixed. Therefore, we switched over to type 1 and were able to achieve very good strengths. So type 1 cement was used for the remainder of our tests. Water, right around 18 to 25% by volume was used, and this equated to a water to binder ratio of right around 0.2 to 0.3. And this is pretty typical for any UHPC. Coarse aggregate also, towards the end of our mixes, it increased upwards of 30%, and that was an important property for us because that's gonna drive the cost down because it's taking up a lot of our volume. And the fine aggregate topped off at right around the same 25 to 30%. The aggregate distribution was calculated using the Abrams power law. On the left is the diagram of a passing grading curve where Q of 0.45 is in orange and Q of 0.5 is in green. The yellow dashed line is our mixed aggregate. So it follows Q of 0.4 and Q of 0.45 very, very closely. The coarse aggregate we used is 1/2 inch granite and fine is a combination of quartz and mason sand. It's also important to note that all of the aggregates used in our concrete are from a natural quarry here in Chicopee, Mass, out of Ondrick Natural Earth. This is our compressive strength analysis of mixed QME. So we achieved over 10,000 psi after 1 day with steam curing, and this was done to mimic the steam curing practice in the field that's used by the pre-stressed concrete industry. So what we did was we put it into our curing oven at a temperature of 70 degrees Celsius before we tested after 1 day. Also, it's noted that the industry tends to achieve right around 5,000 psi within 24 hours when releasing their pre-stressed wires. So the strength that we achieved is double that of what they're seeing in industry. This slide looks into our tensile strength calculations and findings. Pictures on the left are pre and post test with a little zoomed in image of the crack propagation that happened. The diagram compares our ECM, which is shown in dotted orange and dotted gray, to regular concrete. The modulus of rupture in terms of PSI of regular concrete was calculated to be 529. The ECM modulus of rupture found to be 1,274. This is 2.4 times greater than regular concrete. So for fracture energy, in terms of pounds per inch, regular concrete was right around 1,717, where ECM came in at 3,752. This is right around 2.2 times greater than regular concrete. The next step in research here at WNE is to look into researching more about that third prong in durable concrete, which is high fracture toughness. And this will be explored by including fiber reinforcement in our ECM, and will be played with between steel fibers and synthetic fibers, both to be considered. This is going to increase our tensile strength and help against crack propagations found in concrete. I'd like to take the time to thank Transportation Infrastructure Durability Center for funding for this research opportunity. And I'd also like to thank my research professors, Dr. Lee and Dr. Shin, for this opportunity that they've given me to work with them on this project over the last 3 years. I've learned a lot, and it'll be valuable to wherever I end up in industry. I hope, future students of theirs can get as involved in this project and progress it as myself and other researchers have done here at WNE. Now I'd like to take the time to answer any questions anyone has about this project.